Starting off with chapter 3, we have 3.1, maximum and minimum values. And we're going to go over some definitions and theory to start off with, and then we're going to see how can we bring the calculus into the mix. So I always have a few drawings. We're going to start off with some function, f of x, and we're going to define it over an open interval. So I'm going to make it a little more interesting for myself. So something like this. And if this is f of x, and I want to define it over an open interval, usually we're speaking anything. I mean, it can be negative infinity to positive infinity, but it could also be just a single set of x values as well. So you don't have to go out to the infinity. So I'm just going to keep it open everywhere before I specify. So what we want to look at, let's see if we can mark a few values for ourselves. Let's see if we can mark an A. That's another x value. We'll say a B maybe, and then a C. I mean, you could call it x1, x2, x3, but we want to keep the definitions less complicated. So a lot of times when we mark x values, what's the next thing we do is we see what's the corresponding y value. So usually when you do that, you go straight up to the function. And if you're naming that point, you could call that a, and then the function evaluated at a. I meant A. Could do the same thing for B. We have the point B. And then the function evaluated at B is the corresponding y value. And then similarly, you can figure out where you are on the function at x equals c. And you have its corresponding y value, f of c. So you kind of notice I chose these points, and they tend to be popular points. Maybe you recognize from your pre-calculus class, we have special names for them. Maybe we haven't really defined them with formal definitions, but a lot of you would say, oh, there's maxes and mins happening. Or maybe I should say maxes and a min happening. So I just like to point out, we're going to define points that look a certain way as local maximums. In our case, we have plural. And this would be the y values, f of a and f of c. Can also do the same thing with our local min. And that would be f of b, the y value where x equals b. Now, maybe you haven't heard the word local before. Why are they using that to describe this? Well, what they're trying to say is you're looking at the word local because it's the highest and lowest value in the neighborhood. So kind of note this for yourself. What we mean by neighborhood, we're looking at the x values. So I'll kind of note that. It's not bad to have in your notes. Highest. Well, I should probably rephrase this. Why are we saying local? Local, because we have the highest or lowest value in, and we kind of also use this in quotes, neighborhood. You may take a few math classes later and they they have a more fancier way to describe neighborhood. Actually, it's commonly used in math, but for our purposes, we're just going to look at what's happening particularly really close to these values. So that's what we mean by neighborhood. If you inspect all of the y values, you will notice that A is the highest. But if you go in this neighborhood around the B, you inspect all those y values, B happens, the f of B happens to be the lowest. So just kind of keeping in mind, local. Got to make sure we include that in our language. Now, there's also something to understand when you're looking at an open interval, depends on where your endpoints are. But we're just considering this entire interval of our function. You will see notation referred to as absolute maximum or absolute minimum. And so it's probably what you guess is going to happen. When we talk about absolutes, and I'll define this a little bit later. Usually we have a better idea when we see a closed interval, the next drawing down. But usually we're kind of looking for the highest of the highs and the lowest of the lows. That's the way I like to think about it. So when I look at the absolute maximum on this open interval, I'm really eyeing this f of c value. That appears on the entire graph. That should be the highest y value we will see. So that's what I'm going to define that as when I'm viewing this. Now be careful. A lot of times when you look at absolute minimum, remember it has to be the absolute min. So the lowest of the lows on the given interval. Some people might start looking at the f of b and have a question about it. Well, can that be the absolute minimum? And my answer to that would be no, because when you look at the rest of the function, there are y values that are much lower than this. So in this case of our particular example, we do not have an absolute minimum. So we would write none or not applicable, just making sure that you address it. Don't leave it blank. So now that you have a kind of an idea, we just threw the word local in there. We threw the word absolute in there. Let's kind of take this to not really the next level, but just trying to understand what's happening when we close off our interval. So if I can talk about a closed interval, I have clear values, or clear endpoints for the x's. So I can see if I can write this down. Nice interval notation. And I'll draw another example, a little bit different, play around with this. So let's say our closed interval starts at A. And keeping in mind, we'll do something on the rounds of this. And then let's just say our function ends at B. And that's actually what we're trying to define as the closed interval. Now, it doesn't matter what's happening beyond. The function can do whatever it wants. Well, that wouldn't be a function on that right side. Sorry about that. Got a little excited. But the function can behave any way it wants outside of this interval, but we're clearly only looking at the function at this snapshot of x's. So now when we start defining values, you might be interested in kind of looking at maybe we care about these high points and low points again. So let me call that, I'm running out of letters. I'll call it K, start in the middle of the alphabet or so. Let's look at this one. We can call that M. And then maybe an N or something. You can kind of name them as you want. I know I can name them a bunch of different X values, but it tends to get messy. So if I'm kind of interpreting what's happening just by looking at this picture, I could definitely talk about the local min and the local max. Again, notice I abbreviated. It's kind of convenient to do so. So I have the local max. Do I have more than one or do I have one? Well, when I look at the two neighborhoods or the three neighborhoods, I'm seeing all these high points, these maximums. So if you're reaching a local max, I believe we should have the function evaluated at k. That's a high point. And this case, the function evaluated at n. And then if we have local minimum, you can kind of see, oh yeah, we can look at this. We have ourselves a local min. Right away we see, oh yeah, f of m. So a lot of times when we keep asking, there's more than one local max, there's more than one local min, or when we want to refer to all of these together, a lot of times you will hear the author or someone ask you, what are the local extrema? And that's just kind of referring to the extreme points of the function. That kind of makes sense, the high points and the low points. If you were, I guess a side note, if you really care about English, you know how we kept saying absolute, I said local maximums. You could technically refer to this, because there's more than one, you can call this the local maxima. So just in case you hear it that way, it's okay to speak with S's or A's. It sounds fancier, I guess, when you use the A at the end instead of the plural of the S, but it means the same thing. A little Latin there. So now we want to get into, let's talk about this absolute max, absolute min. So let's see if we can label those. So let's look for the highest of the highs. The absolute max in our case is going to be the f of k. Makes sense? Okay. And then if we have the absolute min, this is what we have to be careful about. It may not look like a nice low point, but this is where we care about the endpoints of the interval as well. So if I were to name them, or name where the absolute min is, it's the lowest point on the function in this closed interval. And right away, I'm eyeing this point right here. That is the lowest point of the function in the closed interval a comma b. So that would be my function evaluated at the right endpoint. And again, if we're going to refer to both of these at once, guess what? Instead of local extrema, they would be called absolute extrema. Just in case you're reading around, extrema. There we go. So you want to be careful. You kind of notice whenever we're dealing with the absolute part, usually what you have to do is look at the high points and the low points, but also evaluate the function at the two endpoints. That's something new we'd have to play with. That's going to be a little different. And just kind of compare all those y values, and then you'll be able to answer the question, who are your local extrema versus who are your absolute extrema. And so I just want to be careful. Also, one last thing. The reason why they don't like to mention the endpoints as candidates for the local max and local min, kind of what we said earlier. we don't really know what's happening outside the function. So we don't know if it goes up again and then it goes down again or even lower. So the endpoints, they're not allowed to be candidates for local maxes or local mins because you cannot have any way of understanding who's outside of A and who's outside of B for the X values. Also, it kind of ruins a test we use later, but we won't get into that right now. So if you were viewing this function, you might ask yourself, what do I think the most important parts are, or the most important points of the function, excuse me. And a lot of times people care a lot about when something hits a maximum or when something hits a minimum in a certain neighborhood. So you may also refer to local extrema. They tend to imply some interesting behavior. They're important points, but sometimes we call them critical points. And, important, critical. But our author here, Stewart, uses a different vocab for this. Sometimes when you read different calculus books by different authors, they have their own way of explaining, their own style. We're going to use the idea of critical numbers. So we're going to use also known as a critical number. And those are going to be the theme of what we're trying to find here. So a lot of times we want to be very careful. Our author is going to break down, when you use the word point, when you use the word number very freely, you're not being precise. So if we kind of play around with the definition a little bit, see how Stewart, that's our author, is using the word critical number. And so I kind of like to define it with a quick picture just to kind of give us an idea. But it's giving us a hint of what it means. But we can now bring some calculus back into the picture. I know you're wondering when we're going to do that. So if I can kind of give you a quick sketch again. I always like to have the visual, so we'll do something nice like this. So here's our function f. And let's look at this particular value right here. Okay, so that's the function where x equals a. And so we know that there's a y value, x value. So f of a, or if you like to write it as an ordered pair, totally okay. A comma f of a. And so when we talk about the difference between a critical number, a critical value, and a critical point, it really has to do with, are you naming the specific x coordinate, y coordinate, or the whole point in general? So to be speaking, critical number, in our case, so critical number will be known as the a, and that is the x coordinate. Now, critical value is the value of the function at x equals a. It kind of makes sense the way they define it. That is f of a, and that is the y coordinate. And you're going to put these all together, and now we get to define our critical point. And that could make sense because when you do refer to a point in 2 dimensions, you have to have an x value and y value. Whoops, sorry about that. We zoomed in a little bit, got a little excited. So we should have a comma f of a. That is our critical point. So sometimes when we refer to critical numbers, sometimes they care only find the x values or actually only find the y values that might be applicable, or do they want both of them? Now, referring now to calculus, if you remember how to interpret derivatives based on the original function, remember that the derivative at a certain point is defined as the slope of the tangent at that certain point. So remember how we did those graphs where we were interpreting the drawings? Well, you might be specifically interested in what is happening at the critical number. What is the slope of the tangent line at that point? And you can kind of say, oh, it's horizontal. Ah, it's 0. So this is where the definition comes into play. A critical number of the function f if either the derivative evaluated at that value is equal to 0, or everyone forgets this part, so don't forget this part, heads up, or the derivative evaluated at that value could be undefined. And we use A in terms of defining everything, but I think the convention of why they called it C, I mean, you could name it whatever you want to, but guess I'm guessing, I hope that they're being logical, C in critical. So kind of reminds us of critical number. But feel free, it's the X value where the derivative is 0, or the X value where the derivative is undefined. So it could be either or, it could be both, because it could be more than one critical number in the entire function. So kind of keep that in mind. So we have a few new definitions, brought the calculus back. Now let's play. Let's actually apply this to some of the functions that we've already maybe explored in our algebra class. So example 1, find the critical numbers. And remember, I'm thinking, okay, critical numbers. And so every time that comes into play, I'm asking myself, basically, where is the function, the derivative of the function equal to 0, or where is it undefined? So when that comes up, you should always ask yourself this question. And so then the next natural thing to do is let's take the derivative, and we can. So this is a nice polynomial. So the derivative of f of x, 2 times 3, 6x, minus 4. And here's the new part. Remember when I was talking to you in chapter 2, remember how I said it's really nice if you can clean up the derivative as much as you can, because sometimes you have to use it for something later? Well, now is later. So what we do when we're trying to find the critical numbers, remember, it's where the derivative is equal to 0. So the next thing you do is you set whatever that function you found for the derivative, you set it equal to 0. And then the next natural thing you do is, oh, if I have an equation, I try to solve it. So what does that mean? If we solve it, moving the 4 over to both sides, dividing both sides by 6. And then if we want to, be nice, a lot of times reducing is a very good thing. So we can say x equals 2/3 is a critical number of f. Let's write that a little nicer. And the reason is, if you took the derivative of the function and evaluated it at 2/3, you would get 0 back. We kind of looked at it backwards in a sense. We started with the derivative equal to 0 and we found that x. But now, of course, function notation says, let's go backwards, let's plug it into x, and you do get the same thing. So kind of keep in mind your final answer you would circle or enter, depending on what we're using this for. So now that we kind of understand the concept of the critical numbers, what we want to make sure of is, let's see if we can apply this to all the different functions we've ever seen in chapter 2. So that's where part B comes into play. So again, if we're finding the critical numbers, remember, it's where the derivative is 0 or if it's undefined. So what we want to do first is say, let's first just try to take the derivative of this function. And right now I'm always looking at the rewriting part. The first thing I do, I see that radical, and that tells me x minus 1 to the positive 1/2. I didn't take the derivative yet. So now the next step was, let's take that derivative. See if we can write that. So the derivative, let's see, we pull the 1/2 around the front. Derivative times x minus 1, we say 1/2 minus 1, which gives you negative 1/2. And I guess if you were looking at the chain rule, it is a little more complicated than just an x, but lucky for us, the derivative of x minus 1 is just 1. So yeah, I mean, it's a good habit. So then if we know we're going to do something with this derivative, a lot of times we really care about saying, okay, let's make it prettier. Let's rewrite it. Perhaps if I know I'm going to use it, I'll probably rewrite it so that positive exponents are in play. And when I move to positive exponents, I also want to make sure if I have fraction exponents, I rewrite it in radical form. So what I want to be careful about, again, that is my derivative of my function in general. And we care where it's equal to 0 or where it's undefined. So just a little hint, and I know you probably never thought about it so much before, but I'd like to point it out because we tend to use this a lot. We've got ourselves a fraction. You agree? Yeah. So when we talk about, remember the goal, where's the derivative 0? Well, fractions are equal to 0 when the numerator is equal to 0. I know sometimes you're like, oh, that's obvious. Well, not for everyone. So, you know, and a lot of times none of us have done fractions in years because you're so advanced now. So now we just kind of remind you. So you'll be fine. So what I'm looking for, the first thing I could kind of ask myself, where is f prime x equal to 0? That's kind of what I'm talking to myself in my mind. And I'm asking, well, if the numerator is equal to 0, well, that would mean, what's the numerator? In our case, the numerator, which is equal to 1, equals 0. And it shouldn't. Can you solve that equation? No. So, I mean, by the way, numerator equals 1 is never 0. So we know for sure, by the way, our derivative will never be equal to 0. So sometimes you guys stop there because usually that's kind of everyone's favorite part. Oh yeah, I can't solve it, I'm done. But we can't forget the second thing we need to find. We need to ask ourselves, where is the derivative undefined? And so one last thing, well, fractions are equal to 0 when the numerator is 0. Well, fractions are undefined. Let's spell undefined right. There we go. Fractions are undefined when the denominator equals 0. You guys remember the whole, you know, 0 on top was okay because that's equal to 0, but 0 in the bottom is not okay, so that's the no part. It's kind of what brings it back to the front of my mind from my past. So what we want to do is kind of say, oh, we do have a fraction. Let's kind of ask ourselves, where is f prime x undefined. I might need more paper on this one, but I'll go over here. So our derivative is undefined. Maybe instead of saying an equal, it's probably nicer and more proper to say is. When our denominator, which is equal to 2 times square root of x minus 1, is equal to 0. And so now, naturally, have a little fun. Let's solve for this. The 2 will divide out, so we get square root of x minus 1 equals 0. We square both sides, we get x minus 1 equals 0. X minus 1 equals 0, sorry about that. Add 1 to both sides, we get x equals 1. So what happens? We actually found our critical number. Now you could check if you're interested. Sometimes you make a minor mistake and then things don't work out the way they should. If you'd like to check, just kind of make sure you're kind of restating. F prime of 1, is it undefined? You just go back to your original function yourself. Okay, the derivative of the function. And if we were to plug in 1 to the denominator, we get the square root of 0. And then 2 times 0 is 0. So we'd still get a 0 in the denominator. So that's pretty good. We also could ask ourselves, just to kind of remember that sometimes you have to account for, is it in the domain of the original function in the first place? Let's check up the original function. What's f of 1? Go back. F of 1 is what? Square root of 1 minus 1 is equal to 0. And as long as it's a real number, then we're pretty clear. It's in the domain. It's where the derivative is undefined. So we can be clear with our final saying, x equals 1 is a critical number. And I'm only restating this in purposes of your notes, just to kind of help you check. Just kind of be careful. So let me rephrase this one more time. A lot of times people tend to stop when they get to the solution where the denominator is giving you, how do you say, the x value where the denominator is 0. Sometimes people stop and they're like, oh, we're good. But I always make sure that this value is in the domain of the original function before I call it a critical number. So that's kind of what I'm looking at right here. And so maybe if you want to, you could check, make sure x equals 1 is in domain of f of x before calling it a critical number. Sometimes we forget that minor detail. And so what does that mean? Is it in the domain? One more time, this part right here. I'll see if I can kind of say is in domain of f of x. Basically, when you plug it into the original function, okay, because that's who we're starting off with. When you plug it in, do you get a real number back? And if you do, then you are set to call it a critical number. Perhaps I'm just a bit too wordy today, but I just want to make sure there's a subtlety that a lot of us miss. So that's why I lecture on it. So let's see what we can do with another type of example. Just changing the functions as we go, and we can kind of play around. And here we go with an absolute value function. F of x equals the absolute value of 2x minus 6. And I know they're asking for critical numbers, so kind of that gives me a heads up, hey, I'm going to have to take a derivative. But we can't take derivatives of absolute values right off the bat. If you guys remember, the absolute value had a sharp turn. There's a vertex in a way. I guess we don't call it the vertex, but it's a V-like issue. So this is where we go. Let's have ourselves recall what it does mean to be an absolute value. Okay, so remember, absolute value of x. They redefined it as a piecewise function. And I know we're not used to seeing it that way, but calculus is always a big deal. So the absolute value of x is x if x is greater than or equal to 0. And it's the opposite of x if x is less than 0. And that's supposed to give you the idea of the sharp corner. Well, look at it from here. Here's our function. That would be y equals absolute value of x, by the way. So what I want to do is I want to apply this to my more complicated inside of the absolute value. Let's have ourselves rewrite it for a second in terms of this piecewise. So let's rewrite f of x. It's got two pieces. I was a little exaggerating there. I have 2x minus 6. That's the inside. That's the absolute value of x. And that's happening if the inside, 2x minus 6, is greater than or equal to 0. I also have the opposite of the inside, 2x minus 6, again, if 2x minus 6 is less than 0. So this is just trying to relate it to what it means to be an absolute value, but now you can clean it up a little bit. So let's clean this up. We're going to get f of x equals, what I mean by clean it up, I mean, look at the domain part particularly. So we see this 2x minus 6. If you'd like to distribute the negative sign, it's fine. So just kind of solve the linear inequalities to help you out with the domain right here. I'll do one with you just to make sure you're okay. So do it off to the side. Let's do the bottom one just because I have more room. I have 2x minus 6 is less than 0. 2x is less than 6, so that we should have x is less than 3. So that's giving us the actual domain of our shifted, translated function. So similarly, you could do the same. You kind of notice they're both the same, so we should have x is greater than or equal to 3. And so why do we care so much about this or doing this? Well, this 3 right here that we see, it's significant because it's the sharp corner. Or it's the x value, I should say. Location of the sharp corner, which kind of was the reason why we couldn't just take derivative of the absolute value in its original state. So at this point, now that we have rewritten f of x as a piecewise function, where both of those pieces are very friendly derivatives, we can now take the derivative. And if we do that, we have f prime x is 2. F prime x is negative 2, the two different pieces. And we're just making sure that we are listing the domain. So we have x is greater than or equal to 3, or x is less than 3. And so before I move on, I want to be careful my domain is the right place. I remember how we were talking about the location of the sharp corner? Well, if 3 is the location of the sharp corner, your derivative is not quite defined there. So we have to be very careful. So we have to use our eraser. And even though we saw this up here, I'll highlight it in teal. Notice that there's going to be a change. So here I am erasing. I know sometimes we're so used to copying everything over again, but what's the reasoning behind this one more time? Is that we have no equal to. Oh, well, let's write this. Sometimes red is kind of the nice one. So the issue is no equal to 3. And the reason being is that your derivative is not defined at x equals 3. And if you want a quick picture of this, you kind of have the idea. You can graph it and you can see, but we can do a quick little picture. And we say, looks like it shifted over 3 units and it's vertically stretched a bit. So what does that look like? 1, 2, 3, 1, 2, 3. And we've got ourselves the absolute value again. Probably should be a little narrower. I got a little excited there. And the reason why it's not defined is the corner. Remember, derivatives, in order to be a differentiable function, you have to be smooth and continuous. That corner is the issue. So we're kind of analyzing this using geometry, hence the first part of our class, analytic geometry. That's where we get the name from. So if we know that we can't really set our derivative equal to 0 because the derivative in each case was never equal to 0, there's this undefined issue, okay? So we have a feeling, okay, f prime of 3 is undefined, for sure, because of this reasoning. But before we can call it a critical number, just double check one last thing. If you take your original function and you plug in that 3, do you get a real number back? And so what's our original function? The absolute value of 2x minus 6. And you don't really have to physically plug it in. I'm doing this for purpose of notes, but notice we get 0, which is a real number. So we have our second check. This is telling us, therefore, x equals 3, or we can just circle our answer. We don't have to really restate it, but there's a reason you tune in, right? You have some beautiful notes for Calc 2 so that you can refer back to. So x equals 3 is a critical number of f. And so there's not too much computation. I know you see my writing, it's more because I like to explain as I go. But when you look back at the other calculations, those were nice differentiable functions. Sometimes when you see that absolute value, that's where you have to kind of pick it apart and rethink about that. So I think with this, you should be able to completely have a good idea of how to find critical numbers given any of the functions in our homework. Just to kind of have a taste for all of them. Sometimes the derivatives get a little more exciting, but that's where our algebra comes back into play. So before we move on or end the section, we have something that you're kind of already guessing what's happening, but I just want to define it formally and then sum this all up with a nice example so that we're getting all of the concepts of this section together. So let's kind of look at Firmus Theorem. We have, they're reminding us f of c is a local extreme value. If that is the case, then c must be a critical number of f. And it kind of makes sense where if you take a picture and you're looking at your function and you're noticing, oh, I have a max, I have a min, then yeah, there is a critical number happening. So I will also maybe give you like I guess it's kind of pretty, but just kind of makes it sure. At a local min max, just remind ourselves that the derivative is either 0 or it's undefined. So kind of keep that in mind. And you're like, yeah, I kind of remember by doing all these examples before we got to this Firmus theorem. But the only thing I must caution you on is that if you take the converse of Firmus theorem, it's false. And what they mean by converse, remember how we talked about hypothesis? So see if I can relook at this. They always talk about the if part first, that's the hypothesis. If all of these criteria hold, then we can automatically assume that's our conclusion. So the converse is flip-flopping the hypothesis with the conclusion. So if you figured out you had the derivative was 0, or you had a critical number, it's not the case always that the function evaluated at that critical number is a local min or local max. And the reason behind this is because it's the case that everyone usually tends to forget. Remember, if you're trying to be a critical number, your derivative is either 0 or undefined. Everyone forgets about the undefined part. So a lot of times when you end up proving in your other math classes to come, sometimes if you know that something's false, or maybe you studied and you already kind of remember it's false and you're trying to prove it, all we have to do is come up with a counter example so that we can disprove whatever that statement is. So like one of the ones that I kind of know off the top of my head, and I pick really simple ones. I mean, simple for being in a calculus class, not simple to everyone, but I pick like x cubed. That's a very nice one to take the derivative of as well. And, you know, we can find the derivative, that's fine. Little calculations, so that's equal to 3x squared. And a lot of times when you're doing that, you're setting it equal to 0. What happens? We get x squared equals 0. Or x equals 0. And so we could kind of say, okay, yeah, that is true. We have a critical number. It is a critical number because it's where the derivative is equal to 0. But if we look at this a little bit clearer and maybe analyzing the geometry behind this, okay, so just kind of keep in mind, critical number, what does that mean? That means the derivative at that point is equal to 0. Okay, so let's look at the actual picture of the function. And we could pull our TI out at this point. I don't want to do that at the moment, but I know how to draw these already, but you can verify. So there's your cubic function. And so you know how you have a critical number because the slope of the tangent line at that point is 0. But if you look at where f of 0 is, is still equal to 0, it's not a critical, you say, it is a critical number. It is not a local min or a local max. Do you see a high point? Do you see a low point? No, we don't. And you can play with the different functions to see what works. But just be careful. Most of the time, you're not having to think backwards, but I do feel the need to sometimes mention it. Every once in a while, people tend to get the wrong idea. So I try my best. So we're almost there. Let's sum everything up. For those of you that like steps and recipes, you're gonna love this section and the next section. We're gonna look at basically, how are we looking for absolute extrema of a function on a closed interval a, b? And if we're gonna do this, we had our pre-calculus way, but that usually involved, if it was a complicated function like a polynomial, you had to kind of use your TI to figure out all these values. But now we have calculus. So 4 steps to check for, or checkpoints along the way. First thing you're going to try to do all the time is find the critical numbers. What does that usually involve? Finding the derivative, and where the derivative is equal to 0 or where it's equal to an undefined number. Probably said it wrong. Where the derivative is undefined is a lot nicer way to say it. My apologies. Okay, so once we have that, a lot of times what you want to do is find the corresponding y value to your critical number. What do we call that again? Our critical value. And the last thing before we make our conclusions is you're basically going to find the y values of the endpoints of the interval. And when you do that, compare all of the y values, and the largest value we get from the steps 2 and the steps 3, or step 3, is the absolute max. We mentioned it, but maybe not so formally when we were going over the first example. And you're thinking, okay, well, what does this mean? The smallest value must be the absolute min. So we can figure all this out without even having to draw the picture, which is very powerful. I know we kind of went over polynomials in pre-calculus or college algebra, and we kind of had to have an idea of what the polynomial was behaving like, and we had to use our TI to determine mins and maxes. Well, now we have calculus, and it goes a lot faster. So I have just the thing for you, a polynomial. First thing I'm going to do, I'm just going through step 1, finding the critical numbers. What does that involve? Calculating the derivative first. The derivative of 2x cubed is 6x squared. Derivative of negative 3x squared is negative 6x, and then minus 12. So we are going to, we notice it's a polynomial, so it won't be undefined. So we will set it equal to 0 and see if we can find those corresponding x values. So when I look at it, it's a nice trinomial with a degree of 2. And see if I can factor it. Sometimes that makes my life easier. If you don't like factoring, then there is the quadratic formula you can bring back to life. But I'm kind of happy here because I do see a 6. So if I pull that out, I get an x squared minus x minus 2, still equal to 0. And then continue factoring if possible. I believe this is a nice one. Factors of negative 2 that add up to negative 1. We have x minus 2, x plus 1. And then, remember the 6, it divides out. It's not attached to any variable. From this, we should get x equals 2 or x equals negative 1. And The one thing I want to pay attention to, if I am on the open interval, negative infinity to positive infinity, both of these values would be valid to talk about critical numbers. However, this x equals 2, I'm going to ignore it. I don't really need to consider it because 2 is not in the interval negative 2, 1. Remember, they wanted to define the interval for us. I mean, so cool. That saves me some time, at least. If the interval was a little larger and it did include the 2, then we would have to just consider this as well. So a lot of times I'm still looking at step 1. I found the critical number. Okay, so note x equals negative 1 is a critical number. So that was all part of step 1. Step 2, kind of going with this, we are evaluating f at the critical numbers. So find, and then this will be what we call the critical value. What does that mean? F of c, or in our case, f of negative 1. And it is a polynomial. I could get the TI out, we could use our tables, but you know, the numbers do not seem that horrible, so I'm gonna power through. Feel free to double check yourself if you need to. Sometimes the biggest mistake is you thinking that you can do this in your mind and then you miss one little negative sign and it throws yourself off. So feel free, write out another step or so. A lot of times I like to show what happens when I take my negative numbers to power, just so to be clear. And so I should have negative 2 minus 3 plus 12 plus 1. And we should get ourselves, I believe that's an 8, 6. Yep. I always have to think about it. Okay, so right now we don't know what to do with that yet. We're gonna wait. I do wanna go through looking at what is the value of f at the endpoints. That'd be like step 3 in a sense. Evaluate f at the endpoints. So what does that mean? Remember, we have the interval AB. In our case, the interval is negative 2, positive 1. Yeah, there we go. So when they talk about at the endpoints, you're basically asking yourself, okay, what is f of A and what is f of B? I'll leave some space just in case. But in our case, we're not talking about f of A and f of B. We are actually saying what is f of negative 2. Well, let's plug that in. And remember, you're plugging it into the function. The reason why you're taking the derivative is because you're analyzing the original function. So be really careful. So what do we have? 2 times negative 2 cubed minus 3 times negative 2 squared minus 12 times negative 2 plus 1. What do we have? 2 times negative 8 minus 3 times 4 plus 24 plus 1. And I know you're probably more advanced and you're skipping steps. That's okay. I'm just trying to make sure that we're clear on this one. So I have negative 16 minus 12 plus 24 plus 1. And maybe now I can kind of use my calculator if I need to. I believe I should have a negative 3. So let's wait before we do anything. We still got to calculate f of b. And what is that? The function evaluated at 1. I thought we just did that. Oh no, we did -1. So one more time. And this is where, because we're writing so much on the paper, it's really easy for your eyes to skip over something. So I constantly look back at my original function and compare. And I always want to make sure I'm not missing any signs or I accidentally write a number wrong, which is really common in our class. We're so focused on some of the more complicated things that sometimes all of the arithmetic kind of passes by us. That's how you know you're advanced. Okay, so what do we have? We have 2. Oh, positive ones are very nice to cube and square. 2 minus 3 plus 12 plus 1. Take your time on this, but I have a -12. -12. Okay, so there's a little bit of work here. And, you know, yes, you could have made it easier, just plug it into your TI, that's no problem. But what I'm looking at is the 4th step. This is where I'm comparing all the y values. Okay, so what do is I just go back and I say, okay, this was my y value. And here's another y value. And here's another y value. And a lot of times they like to consider this in terms of the critical point. So it's not a bad idea just to mention it all at once. Perhaps they'll be more specific. Do they want the x value? Do they want the y value? You can't go wrong usually when you mention it all together because you actually have more information than what you need. But certain applications, you care more about x, y. X or Y, I should say. So let's kind of go back and see. Right away, who's our largest? 8, -3, 12, oh, the positive one. So hey, note to self, we got the largest one. So right away, I can go back and say, okay, therefore, my absolute max is located where f of -1 equals 8. Now, I just go through and say, well, who's smaller, -3 or -12? We will answer, -12 is the smallest. So now we have our absolute min. And just to kind of be clear, just name the entire expression, I should say equation in a sense, or the entire point. F of 1 is equal to -12. So I know you've been through a lot more complicated stuff than this. It looks threatening when you do look at the page, I do understand. But the main thing is we're just building off of finding the derivative of a function and what are we doing with the derivative and what types of information about the original function is it giving us. So go ahead, follow the recipe, practice, 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 and I will see you in the next section.